This is the third video on rotation. We're looking at how to find the rotational inertia of a spinning bar, and this is being done experimentally. Here is a picture of the experiment. We have a bar at the top here with two masses on it, and we're causing it to spin through a spindle in the middle with a pulley type system with a rope around it. The rope is then run over another pulley down to a small mass. The mass provides a torque on the pulley by providing a tension force in the string. So we've got a tension force in the string, and that's provided by the mass going downwards with its weight force or gravitational force, and it's accelerating downwards. So that's essentially the experiment. There's another view shown of it here, and you can actually see the masses used in the diagram. So let's have a look, because what we need to do is work out a number of things to be able to work out how the bar is spinning. One of the things we will need to know is the torque on the bar, and to know the torque we will need to know this tension force. So let's work with a slightly simplified diagram. Here's the pulley that rotates at the edge. We have got a tension force here, and over this smooth pulley, we're going to assume there's no friction in the pulley, we've got a mass, and it's accelerating downwards with an acceleration of A. Now, if we look at that mass, if it's accelerating downwards, according to Newton's second law, there must be a net force on the mass, which will equal the mass times the acceleration. So we need to work out the net force. On the mass itself, we have got its gravitational force pulling downwards, and we've got the tension force pulling upwards. So if it's going to accelerate downwards, F net will equal the gravitational force minus the tension force. But what we're actually interested in is the tension force. So let's rearrange the equation, and we get the tension force equals the gravitational force minus F net. Now, if we put in what we know then that the tension force will be the gravitational force, which is mass times gravity, minus F net, which we know is mass times acceleration. So from that, we can work out the tension force that is causing the torque. The other thing for working out the torque is to know the radius that that tension force is moving at. And we can actually physically measure that, and that's the measurement of the radius. So we know that the torque equals the tension force multiplied by the radius, and we've actually got a measurement for the radius. So we get torque equals Ft times R. So that's how we work out the torque. So we've got the torque that's causing the bar to rotate and spin. Now that bar is rotating and spinning, but we need to know a little bit more. We need to know how that bar is rotating and spinning. Because the small mass here is accelerating downwards, the bar must have an angular acceleration. It will start from stationary and then it will accelerate. But we do need to be able to work out that angular acceleration. So what we have got to do is do the experiment and take some measurements. Now the two measurements we need is the time of the fall, which will equal t, and we need to know the distance of the fall, which we will equal d. And if we measure those two in one way or another, we also know that the initial velocity equals 0, because we'll start from rest. If we have those three things, we can calculate the acceleration of the falling mass by using d equals VIT plus a half AT squared. We know that VI equals 0, so we can simplify that and say d equals a half AT squared. Rearranging, we can get A equals 2d divided by t squared. Now we're measuring the time, and we need the distance of the fall. The easiest way when doing this particular experiment is to allow the bar to spin or rotate 5 times. In other experiments, we may choose to physically measure the distance that the mass falls. So let's look. If we assume we're going to allow the bar to rotate 5 times, if the bar rotates 5 times, that will give us 5 times 2 pi radians. So the 5 for the 5 rotations, 2 pi because there is 2 pi radians in one circle, in one rotation. So that will equal 10 pi radians. We also know that d equals r theta. So for what we're going to do with this experiment, d will equal r, which was given on the previous slide, multiplied by 10 pi. So if we look on to the next slide, here is a set of data. I think it's a student set of data from the previous year. And what we've done, or what the student did, was take different masses, and for each of the different masses, measure a time. And from that, we're going to go through and calculate the torque, and we're going to calculate the angular acceleration. So the angular displacement here, always the same. We allowed it to rotate 5 times, so that was 10 pi radians, which is why we've got the 31.416 radians. The angular displacement is measured in radians. We've got the radius here, which we measured previously, and then we're working out the linear acceleration of the falling mass, and that was shown to you how we did that on the previous slide. So we've calculated the linear of the falling mass. Having got that linear acceleration, we need to calculate the angular acceleration. From one of the earlier videos, we know that our A equals R alpha, so alpha equals A divided by R. Now we've got A here, and we've got R here, so we can do that very easily, and we end up with these numbers here. Tension force, we calculated previously, remember, Ft equals mg minus ma. We've now got A, and we know m, and we know what g is, so we can calculate that one easily enough. And the torque, if you remember, is Ft times r. So that's how we've gone through and calculated each of these parts. As you can see, this has been done on an Excel spreadsheet just by sitting in formulas. You can do all the calculations in a table manually, just, well, maybe not as easily, but you can do it manually as well in a table. If we take that data and we plot the graph, and what we're going to plot is torque against angular acceleration. Those are the two. That's why we've been calculating those two. So if we look at the torque against angular acceleration, we end up with a straight line graph. If it's a straight line graph, we know that the things are directly proportional. So we know that torque is proportional to alpha. And that looks horrible because we use the same symbol for proportion as we do for angular acceleration. So maybe I should write it in words. Torque is proportional to angular acceleration. And we have a graph there. Let's just look at the detail of the graph a little bit more. If we have a graph like this, we know that if torque is proportional to angular acceleration, we can actually get an equation of the line. We can say that the torque equals some sort of constant times the angular acceleration. So having got this constant times the angular acceleration, this constant is the gradient of the line. So that's what we've got, is so torque equals the gradient multiplied by alpha. Now, because I did this on Excel, I actually asked it to give me the equation, which it did, but it gives it in terms of y and x, which is not acceptable. But we can see that the gradient is given here. So instead of using y and x, we must use the torque and the angular acceleration. So we can say torque equals 0.0051 multiplied by alpha. So that is the equation of the line. I had the computer calculate the gradient, but you can calculate the gradient using rise over run as you would normally do. If we compare that by torque equals I alpha, which was the equation about torque on the previous video, we can see that I equals 0.0051, and the unit for inertia is kilograms meters squared. So the inertia of this bar system, and the bar with the two masses tagged on the ends as it was, is 0.0051 kilograms meters squared. And that is how you can work out the inertia from an experiment, from taking experimental measurements of something that is spinning. The important things you need to be able to do is measure the tension force, the radius, so that you can get the torque, and then measure the distance of the fall and the time, so you can calculate the acceleration of the falling mass and hence get the angular acceleration. That's the end of this video.